So welcome to the next lecture. In this lecture, let's start with estimation. So we call it statistical estimation because we are trying to estimate quantities, but we are trying to estimate them using statistical procedures. So in this lecture, we'll talk about two types of estimation: large sample estimation and small sample estimation. In this first lecture, we'll discuss large sample estimation, and in the second lecture, we'll discuss small sample estimation. So let's start with the common sense of what estimation really determines here. So until now, we discussed probability and we discussed the statistical quantities that are generally mentioned in terms of probabilities. Now we want to know the difference between probability and statistical reasoning. So in the last lecture, we talked about sampling, and we started with a population and we imagined that there might be many samples, and we investigated how sample statistics were distributed in terms of what we call sampling distribution. But in this chapter, we'll try to do the reverse. We have a sample and we are trying to estimate what was the random system that generated its statistics, and we try to shift our mode of thinking towards deductive to inductive reasoning. So remember that deductive reasoning is where you go from a hypothesis to a conclusion, but inductive reasoning is going backward, where we start from a set of observations and we try to come towards a reasonable hypothesis. So probability is a process of deduction where we start with a hypothesis and we come to a conclusion. But statistical reasoning is the reverse, where we try to take the sample and we try to estimate what would be the values in the population based on the sample. Why would we do that? Say for a simple example, let's say I have a given sample here, a given population here. Let's say this is the population of all people with let's say rheumatoid arthritis. Now the problem with this disease is that there are many people that have the disease and we cannot test. Let's say for example, I have a drug here that I have developed and I want to know whether it is effective on people with rheumatoid arthritis. Now the question comes back, which drug would I choose and how do I know that this drug is effective or not? Is it effective or not? Now, understanding the effectiveness of a drug itself is an understanding of how deductive reasoning or inductive reasoning works. Because we cannot test it on the total population of every person with rheumatoid arthritis, what we do is we take a small sample from that population. Remember that we are basically taking a small part of that population and we are testing this drug on this sample. Once we check the drug on the sample, if it is effective, so we'll put a tick and then we'll try to estimate if, for example, let's say in the sample we took 100 people and it worked out of 95 out of 100. Then we'll try to deduce what would be the probability that it works on the population. So this is the concept of inductive reasoning. So this is the process of inductive reasoning, where remember that we started with the sample and we are trying to estimate what would be the effectiveness of this drug here in the population. So this is the process of inductive reasoning. So before, remember that we started with population statistics, and from the sample statistics we try to calculate the sample statistics from the population. Here we start with the sample and we try to estimate what would be the effectiveness in the population, or what would be the probability or the statistical parameters in the population. Now remember, the term population here used in statistics represents all possible measurements or outcomes that are of interest to us and in a particular study or a piece of analysis. So the term sample here refers to the subset of a population that is selected for analysis. For example, if you are taking in say all all people with a certain cancer, that would be the population. For example, let's say if you're taking people with carcinoma, what is the total population there? And sample here is taking people that specifically we know want to test a particular drug or a therapy on them. So that is basically called as a sample. So choosing a small part of the population is called a sample. Now again we'll come back to the process of sampling. In choosing a sample, it is really important that it represents the population, which means number one, there should not be any bias. Number two, there are a number of sampling methods that are available to ensure that your data is representative. One of the most straightforward examples is simple random samples, is the most straightforward of these methods. Let's discuss parameters. Remember that parameters are statistics of a population. So populations in general are described by their probability distributions and or their parameters. For a quantitative population, the location and the shape is determined by the mean and standard deviation. If you have a binomial population, it is determined by one parameter, the probability of success. So if the values of parameters are unknown, what we try to do is we make inference. Inference here is, in crude language, we call it a statistical guess about them using the sample information. So there are two things, the two types of inference that we generally look at in this chapter, in this subject or in this course. So the first one we are going to look at is estimation. Estimation is basically trying to estimate or predict the value of the parameter. So what are we trying to question here is what are the most likely values of mu, sigma and p. In hypothesis testing, we decide the value of the parameter based on some preconceived idea, for example from another test group or another study, and we'll try to see if that works with this particular sample or not. So did the sample come from a population with mu equal to 2 or p equal to 0.3? This is hypothesis testing. So hypothesis testing, we already have a preconceived idea. For example, let's say if you're trying to compare two drugs for let's say we have two versions of aspirin, and one version of aspirin which is the regular version and one version which is which is under works, and they say that it would be a little more effective than that. So what do we do here? We try to compare the new one with the old one. So we already know the statistics for the old one. We are going to compare the statistics of the new drug with the statistics of the old drug and see if it is better at relieving headaches than the old drug. So this is the idea behind hypothesis testing. In estimation, we are basically trying to estimate or predict the values of the parameter using statistical methods. Now, so let's take an example. Let's say if a consumer wants to estimate the average price of a similar home in a city before putting his home in the market, he'll try to estimate the mean price of the average price of a home. What would be an example of hypothesis testing is that, let's say a manufacturer wants to know if a particular type of steel is more resistant to high temperatures than an old type. So his hypothesis test here is the average new resistance greater than the old average resistance. So here they want to know whether mu n is greater than mu naught or not. So here comparisons is generally done, but in estimation we directly estimate the actual value. Now, so whether you are estimating parameters or testing hypothesis, the same statistical methods are important because they provide, number one, the method for making the inference, and number two, a numerical measure of goodness or reliability of that inference. So statistical inference is the procedure by which we reach a conclusion about a population on the basis of the information that is contained in a sample drawn from that population. So remember the term statistical inference. So whenever we say the term statistical inference, we are trying to say that it is inferential but using statistical methods. So we already have a basis of the information contained in the sample drawn from that particular population. So we are trying to reach a conclusion. Estimation here involves the use of data in the sample to calculate the corresponding parameter in the population. Here in estimation, we have the parameters for the sample and we are trying to estimate the parameters for the population. So to do that, we use a value called estimator. So a single computed value is referred to as an estimate. An estimator is a rule. So a rule basically means it's a formula and it tells you how to calculate the estimate based on the sample. The most common understanding of this is a sample statistic here is used to estimate the population parameters. For example, sample mean is an estimation, is a good estimator for population mean, things like that. Now, what are the main qualities, that conditions that an estimator should satisfy? Number one is it should be unbiased, meaning that the mean of the estimator must be equal to the mean of the parameter. Number two is it should be consistent, meaning that the value of the estimator approaches the value of the parameter when you increase the sample size. Number three, it should be relatively efficient, meaning that the estimator for a parameter has to have the smallest variance of all estimators which could be used. So it has to have the smallest variance possible. Now, what are the sum of these unbiased estimators? To estimate population mean, the estimator is the sample mean. To estimate population proportion, sample proportion is a good estimator. To estimate difference between two population means, difference between two sample means is a good estimator. Difference between two population proportions, the estimator is the two sample proportions. So these are some of the common estimators that we use. Now there are two types of estimates that we can use. One is population point estimate, number two is interval estimate. So point estimate is a single value. Interval estimate is a range of values. So it's a range of values. For example, if you get a value just A, we call that a point estimator. But if you get any value from A to B, we call that an interval estimator. So what is a point estimate? It's a single numerical value that is used to estimate the corresponding population parameter. An interval estimate here is a range of values that's used to determine the parameter. Here, for every interval, we are always using what we call a degree of confidence. Degree of confidence is what are the chances that the actual population mean lies in the interval that you are proposing. So every time we take a certain value, we cannot choose 100% confidence, because we will never achieve 100% confidence in any value. So the only way we can choose that is based on statistical values. That statistical chance of having the mean in the interval that you are choosing is called as the degree of confidence. So again, I'm gonna write it down here. So degree of confidence is the probability that the population parameter lies in the interval estimate. So whether the population parameter lies in the interval estimate is called as the degree of confidence. Next, let's talk about the same term, confidence intervals. So a confidence interval is basically an interval estimate with a specific level of confidence. For example, a confidence interval here can be 90% confidence interval, 95% confidence interval, or 99% confidence interval. Meaning that when you choose 90% confidence interval, it basically says that there is a 90% chance that the population parameter can lie in the interval that you are mentioning. If it is 95%, we are going to say that there is a 95% chance that the value that you find, or the population proportion that you find, is in the interval estimate. These are called confidence intervals. So a level of confidence is the probability that an interval estimate will contain the parameter, and these generally depend on the sampling distributions. So, and the shape of the sampling distribution depends on the sample sizes. So that for larger sample sizes, we can use central limit theorem to allow us, so it allows us to use normal distributions. When you have small sample sizes, we need to learn a new distribution. We call that a t distribution. So when we discuss small sample estimation, we will try to work it out, t distribution, what it is and how to calculate it. So let's start with confidence intervals. Let's start with number one, confidence interval for a population mean. Now, there are different types of confidence intervals. For a population mean, for the difference between two population means, for a population proportion, difference between population proportions, confidence interval for variance of two normally distributed populations, confidence interval for the ratio of variances. Now, we will not be discussing number 5 and number 6. We are only going to discuss 1 to 4 because these are the most relevant of all confidence intervals. And this is important because these are questions that are commonly repetitive in competitive exams as well. So let's start with the confidence interval. So the percent of time that the true mean will lie in the interval estimate given is called as confidence interval. So the point estimator for population mean is the sample mean. So a point estimate for population mean is the sample mean x bar. So x bar is given by sigma xi by n. For example, here they have given you a sample of 34 male freshman students and their weights, and they are asking us to give you an estimate of all of these people. Then the sample mean becomes 182.4. So 182.4 becomes the population mean, the estimator point estimate for the population mean. Now for a point estimate for a population proportion P, P cap can be found as x by n. So is the sample proportion is the estimator for population proportion. So which can be written by x by n. So where x is the number of successes and n is the total number of trials. Now let's come to the properties of point estimators. So remember that an estimator is calculated from sample values and from sample to sample according to its sampling distributions. So an estimator is generally unbiased if the mean of the sampling distributions equals the parameter of interest. So it does not systematically overestimate or underestimate the target parameter. So both sample mean and sample proportion are unbiased estimators because they themselves by themselves are not biased in the values that they produce. The data might be biased, but the mean by itself is not biased. So one another estimator that we use is sample variance, is an unbiased estimator for population variance. So that is given by s square equals sigma xi minus x bar square by n minus 1. So this is the sampling. So of all the unbiased estimators, we prefer the estimator whose sampling distribution has the smallest spread or variability. So it should have the smallest spread as possible. Next, let's come to the error part. What is the maximum error of an estimate? So the maximum error of an estimate is denoted by E, and it is generally 1/2 of the width of the confidence interval. So 1.5 times the width of the confidence interval. Remember this is very important. E here is 1.5 times the width of the confidence interval is the maximum error. So the maximum difference between the point estimate and the actual parameter is called as the maximum error of an estimate. Now there are two types of populations that we can talk about. One is the sample population and the target population. Sample population is the one where we have drawn the sample from. Target population is the population for which we will try to make an inference. Now sometimes these two are the same, sometimes these two might be different. So depending on the type of situations that we have and depending on the type of data that we have, it is really important for researchers to understand the difference between sample populations and targeted populations, because understanding the delicate differences between these two can lead you to avoid simple mistakes and avoid common errors that are generally can be produced. So for example, you can reduce unwarranted inferences that you generally get when you are taking from sample and putting it into another target population. So which generally should not be something that should be done every single time, and it should only be used under certain circumstances. Next, let's talk about random and non-random samples. So the strict validity of statistical procedures mainly depends on the assumption of random samples. So what is a random sample then? So a random sample is selection of some members of the population such that each member is independently chosen, has a known non-zero probability of being selected, meaning that every person has the same probability of being selected. So that is a simple random sample. Now the most common ones that are commonly used in terms of confidence interval is 95%. So mostly 95% probability is, if you take it in a normal distribution curve, that generally lies between negative 1.96 sigma and positive 1.96 sigma. So 1.96 standard deviations of the mean. So 1.96 standard errors of the mean is equal to the 95% confidence interval. So when you want to calculate the formula for 95% confidence interval, we can write it as x bar plus or minus 1.96 times the standard error. So this is the formula and this is the estimator. So x bar plus plus or minus 1.96 times the standard error. Now this is good when you have the sample size greater than 30, or if it is less than 30 but it is said to be normal. So these are the only two conditions under which you are going to use this formula. One is if n is greater than 30, and number two is when n is less than 30 but it is said in the question that it is normally approximately normal or normally distributed. So next let's come to the margin of error. The margin of error is generally denoted by sigma x bar, and it is given by margin of error is generally 1.96 times the sigma x bar, or we can simply write sigma by root n. So this here is the margin of error. So this is the value that we generally have as the margin of error. Now 95% confidence intervals sometimes can also be approximated to plus or minus 2 sigma, but you can do both of them. So let's take a simple example. So let's try this problem here. So what is given here? Suppose a researcher interested in obtaining an estimate of the average level of some enzymes in a certain population takes a sample of 10 individuals, determines the level of enzyme in each, and computes a sample mean of x bar equals 22. So we'll write down the data with a variance of 45. So n is given as 10, x bar is given as 22, and variance is sigma square is given as 45. Now here it is mentioned that it is normally distributed, which means that we can use CLT. So CLT from central limit theorem, what is the formula that we have to use here? If you want to estimate again, x bar plus or minus 1.96 times sigma by root n. So x bar is 22 plus or minus 1.96 times sigma here. So sigma here is root 45 by root 10. So when you calculate the value, you have square root of 4.5 when you take it out, and then times 1.96. So you get 22 plus or minus 4.158. So 22 plus or minus. So when you write 22 plus or minus 1.8, what does that mean? You have two values. It's 22 minus 4.158 comma 22 plus 4.158. So you have minus 22, the value is 17.842, and the second value is 22 plus 4.158, that value becomes 26.158. So this is the 95% confidence interval, and this is the estimate value. So the m value here lies between or 17.842 and 26.158. So this is how you can calculate it. So this value of exactly 1.96 is called as the reliability coefficient, and this reliability coefficient is generally calculated from the standard distribution table, normal distribution table. And these are standard values for standard distributions. For example, for 95% the reliability coefficient is 1.96. So you just need to remember that whenever you see 95%, remember that it is plus or minus 1.96. So for a binomial distribution is where we will have to be a little bit careful. So the assumption here is that either NP should be greater than 5 and NQ should be greater than 5, or this condition should be applied. So if it satisfies any one of the condition, we can use the above formulas. So for margin of error here, we have P cap plus or minus 1.96 times under root P cap Q cap by N. So this is the formula for the 95% confidence interval for a population proportion. So let's take the example here that is given. So a homeowner randomly samples 64 homes similar to her and finds out that the average selling price is 250,000 with a standard deviation of 15,000. Estimate the average selling price for all similar homes in the city. So whenever you see the term estimate, we have to estimate the city, the value itself. So the average selling price is X bar is given as $250,000, and the standard deviation sigma is $115,000, and n value is 64. Remember that 64 is greater than 30, which means that we can use CLT. So the estimation here, X bar plus or minus 1.96 into sigma by root n. So X bar is 250,000 plus or minus 1.96 times 15,000 by under root 64. So under root 64 is 8. So you have 1.96 times 15,000 divided by 8. So that gives you a value of $250,000 plus or minus $3675. So when you write the interval, you have 3675 plus 250,000, so which is $253,675, and you have $250,000 minus 3675, which is going to be $246,325. So this is the estimate for the mean price of the homes in that area, and this here is the 95% confidence interval. So remember that we are generally estimating the 95%. If you just want strictly the estimate, this is strictly the point estimate. This is strictly the point estimate. Let's try a proportion problem now. So what is given here? A quality control technician wants to estimate the proportion of soda cans that are underfilled. He randomly samples 200 cans, so n is 200, and x, so it finds that 10 are unfilled. So x here is 10. So P cap is x by n, so 10 by 200, so which is going to be 1 by 20, so which can be written as 0.05. So 1 divided by 20 is 0.05. So from that we know that Q cap is 0.95. So the first thing that we want to do is write down NP cap. So 200 into 0.05. So 200 times 0.05, which gives you a value of 10, which is greater than 5. And NQ cap, which is 200 times 0.95, which becomes 190, which is also greater than 5. So we can use the formula. So the formula is P cap plus or minus 1.96 under root P cap Q cap by n. So this is the 95% confidence interval. So strictly P cap itself is the estimate, but it's the point estimate. So we don't want the point estimate, but we want the actual estimate. So 95% confidence interval, when you write down the value, it becomes 0.05 plus or minus 1.96 under root P cap is 0.05 times 0.95 by 200. So 0.05 times 0.95 divided by 200, and taking the square root of that value gives you a value of 0.05 plus or minus 1.96. So that value becomes 0.03. So you get an estimate of 0.02 to 0.08. So this is the 95% confidence interval for this problem. Now, is it just 95% that generally is used? Most commonly we can use any other types of values as well. So we can find any confidence interval as well, provided we are looking for what is the amount of error. So when you choose a 95% confidence interval, we are assuming a 5% risk of error. So when we use a 99% confidence interval, we are choosing 1% risk of error. So this risk of error is called as the level of significance, and it's written as alpha. So alpha value is generally the one that determines what is the how sure that the probability is. So the lesser the alpha value, the higher the more probability. So 1 minus alpha can be generally most common values used are 0.95, 0.9, 0.90, 0.95 and 0.99. So to estimate it directly, we can use point estimator plus or minus z alpha by 2. So alpha here, remember that for 95% confidence interval, which is generally 0.95, alpha value is 0.05. So when we take the value actually of 1.96, that value is z 0.05 by 2. So that's the value that we took from the table. If you calculate z 0.05 by 2, which is z 0.025, you will get that the value is 1.96. So remember that here we are going to choose this probability. For the probability, you will find the z value. So this is how you can calculate. So I've given a small table for you to simply use this as a reference. So when you want to calculate 90% confidence interval, which means alpha is 10%, then the z value is 1.645. When 95% confidence interval, alpha is 0.05, the z value is 1.960. For 99% confidence interval, alpha is 0.01 and z value is 2.575 or 2.58, whichever is the closest decimal to which you are calculating the answer to. So for the confidence interval, x bar plus or minus z alpha by 2 into sigma by root n when you have a population mean. For a population proportion, p cap plus or minus z alpha by 2 into square root of p cap q cap by n. Let's take an example of this problem here. So you have one sample of size 30 from an electronic component yields the sample mean of 5873 hours with a sigma of 3959. So they calculate a 95% confidence interval. So x bar is 5873 hours, sigma is 3959 hours, and they are having a sample size of 30, so which is okay for CLT. So the formula is x bar plus or minus z alpha by 2 into sigma by root n. Here sigma, they are asking you for 1 minus of 95% confidence interval. That value 95% is equal to 1 minus alpha, so which means alpha here is equal to 0.05. So alpha here is 0. So alpha by 2 becomes 0.025. So the formula becomes x bar plus or minus z 0.025 into sigma by root n. So let's try to find z 0.025. So remember that we are looking for in the probabilities, and for that probability we are trying to look for the z value. So let's take a look at 0.025. So notice this probability right here is 0.025. For that, the z value is minus 1.96. So just don't forget the negative sign. You have 1.96. So the formula becomes x bar plus or minus 1.96 into sigma by root n. Substitute the values. So 5873 plus or minus 1.96 times 3959 by root 30. So calculate the value. You have 1.96 times 3959 divided. So let's take root 30 first. So you have 5873 plus or minus 1.96 into 3959 divided by root 30 value is 5.477. So let's try and calculate now. 1.96 times 3959 divided by 5.477 equals, so you get a value of 5873 plus or minus 1156.54. So if you want the range now, so minus 5873, that gives you 4716.45, and 5873 plus 1156.54 gives you 7029.54. So this here is the 95% confidence interval, and this is how you can calculate any interval values. So use the same principle here. So pause the video right here and try to solve this problem. So use the same principle again. Here in the first problem it's 95%. In this problem they are asking you for the same data, calculate for 99%. So remember that 99% is 0.99, which is equal to 1 minus alpha. So from this alpha becomes 0.01. So we want to calculate z alpha by 2, so which is z 0.01 by 2, which is z 0.005. If you calculate it from the table that I've given previously, the value is 2.575. So you don't need to calculate it every time, just remember the values and it makes it easier. So use the same principle again. So pause the video right here and try to solve this problem. Again, so pause the video right here and try to solve this problem. So use this also as a problem to solve. So pause the video right here and try to solve all these three problems. So they've asked us 90%, 95% and 99%. So with mu of 5.98 and sigma of 3.54 and n of 16. And they've already said that it is approximately normally distributed. So for 90%, the formula for the A part, the formula is x bar plus or minus 1.645 into sigma by root n. For B part, the formula is x bar plus or minus 1.96 into sigma by root n. For C part, the formula is x bar plus or minus 2.575 into sigma by root n. So use these formulas, pause the video right here and try to solve this problem. Next, let's try and solve a proportion problem. Here they have given us n equal to 150 and they said that 104 of the students said that they had played a soccer team. So which means that P cap here is 104 by 150. So which is going to be 0.693 and Q cap becomes 0.307. N here is already given 150. So the formula is for 90% confidence interval. So P cap plus or minus, again Z alpha by 2. For 90% the value is 1.645 into under root P cap Q cap by N. So input all the values, pause the video right here and try to solve this problem. Next, try this problem as well. Here they have given you percentage values already. So the Pew American Research Center has reported in 2003, 18% of internet users have used it for searching information regarding experimental treatments. The sample consisted of 1 to 20 adults. So the percentage P cap is 0.18 and the total N value is 1 to 20. And they're asking you to find a 95% confidence interval. So pause the video right here and try to solve this problem. So pause the video here, use these problems as practice for both for the population mean.